Hello students, today in this lecture I am going to discuss numerical problems related to beta decay what we have discussed in the last class. So come to the first question, first problem. A radioactive nuclei 28Al decays to 28Si through the following nuclear process. So this is a beta decay process. 28Al or it decays into Si28 and it emits beta minus, this antineutrino which is associated with this beta minus particle, and a gamma photon. Masses of these nuclei are given. Mass of aluminium nuclei is this one, mass of silicon nuclei is given, and mass of the electron is also given. They are given in terms of atomic mass unit, and 1 AMU is 931.494 MeV. Now they have given, if the beta minus particle is emitted with an endpoint energy of 2.86 MeV, then calculate the energy of the excited state of 28Si from which gamma ray is emitted. So basically they want to find out the combined energy that is carried by this silicon nuclei and this gamma. Basically you have to calculate the energy of the excited state when a nuclei emits. When a nuclei, what is happening here? This is 28Al. This nuclei emits a beta particle. It will emit a beta particle, this beta minus particle. So here beta minus particle is emitted plus this antineutrino. This is emitted, and this nuclei converts into 28Si nuclei, but this is the excited state of this. This is the excited state of this nuclei. So this nuclei want to go to the lower excited state or the ground state. For this, how can this nuclei go to the ground state or the lower excited state? This is the lower excited state or the ground state of Si. So what will happen? This nuclei can jump from here to here by emitting a photon. This is gamma photon. By emitting gamma photon, this nuclei can jump to the lower excited state, or you can say ground state. So this gamma photon is here. This gamma photon is here written in this equation. So you have to find out the energy of this excited state of 28Si. How can you calculate this? So here we are going to use the Q value. Here we are going to use the concept of Q value. What will be the Q value, or how much energy will be released in this equation? So Q value of this beta minus process, this will be how much? You are aware that for beta minus decay, Q value is given by mass of the parent nuclei, mass of this parent aluminium nuclei, minus mass of the silicon nuclei. This is the deuter nuclei, and these masses are in AMU. So we will multiply this by this number 931. This will be 931.494, and now your answer will be in MeV. This will be the total energy that will be released in this equation. Now substitute these masses. If you substitute these masses, this is 27.981908 minus 27.976929 multiplied by 931.494 MeV. Solve this value with the help of calculator, and you will find out that this comes out to be 4.6379. 4.6379 MeV. This value comes out. So this is the Q value. This is the Q value. From this Q value, we can also write down this Q value in terms of the kinetic energy also. We can also write down the Q value in terms of kinetic energy. This will be equal to the energy carried by this beta minus particle, this antineutrino, and this silica Si plus this gamma photon. So this Q beta value will be equal to energy carried by beta minus particle plus energy carried by this antineutrino plus total energy carried by this silicon, and the energy carried by this silicon plus gamma photon, if we add up these two energy, this will be the energy of the excited state of the silicon we have discussed here. So if we add up the energy carried by this deuterium nuclei and this photon energy, this will be the energy carried by this silicon nuclei in its excited state. This will be our equation. Substitute these values. This is 4.6379. This is in MeV. Here E beta plus E gamma. EB from where we are going to find. This is endpoint energy. What is the meaning of endpoint energy? What is the meaning of endpoint energy? Endpoint energy, you are aware that this endpoint energy from beta particle energy spectrum, and this is always equal to E beta minus particle plus E neutrino particle, antineutrino. This is known as endpoint energy. You can say this is the endpoint energy. So endpoint energy is given 2.86 MeV. This will be 2.86 MeV plus ESI in the excited state. So this ESI in its excited state will be 4.6379 minus 2.86 MeV. Find out this value. What will be its value? It will be 1.78 MeV. This will be nearly 1.78 MeV. So this is the answer of this question. So this is the energy of the excited state of 28 Si nuclei. Now come to question number 2. A free neutron decays into a proton. So we have a free neutron here. This decays into a proton. An electron and an antineutrino. Calculate the kinetic energy shared by the electron and antineutrino given that Mn, masses of Mn, Mp, Me is given. So masses of neutron, proton and electrons are given. So this is the equation basically. So apply the conservation of energy principle. So here we will apply the conservation of energy principle. So for the left hand side, what will be the total energy? It will be rest mass of energy of this neutron mnc square plus its kinetic energy kn. So this will be the rest mass energy of the neutron plus kinetic energy. On this side, this will be rest mass energy of proton mpc square plus kinetic energy of this proton. Second particle is electron, so rest mass energy of the electron plus kinetic energy carried by the electron plus rest mass energy of this antineutrino plus kinetic energy carried by this antineutrino. So here Basically, we have a rest neutron, we have a free neutron which is decaying. So here we can easily assume that this kinetic energy of this neutron is 0. So kinetic energy of this neutron is 0 because this is free neutron. Second is the mass of this antineutrino is 0. So this term will also be 0. So this term will also be 0. And what will be the kinetic energy of the proton? Here this neutron and this proton. So if we are assuming the kinetic energy of this neutron is 0, it means this is at rest. Then this proton will also be at rest. However, it will have a recoil energy, but because mass of the proton is very, very high as compared to mass of electron and this neutrino, so the kinetic energy carried by this proton will also be 0. So these terms will be 0 here. These terms will be 0 here. Now what we want to find out? We want to find out this Ke plus K nu E. So we can rearrange this equation and we can write that Ke plus K nu E bar antineutrino, this is equal to Mnc square. So this is Mn minus Mp, take this Mpc square on this side, so this will be mass of proton, and minus this Me into C square. This will be the formula for the combined kinetic energy of electron and antineutrino. Now substitute these values. Mass of the neutron is 1.00892 AMU or units. Mass of the proton is given 1.007593 units minus this 0.000549. All these values are given in AMU. So how can I find out this? How can I convert this into the MeV? These are the masses in AMU. How can you convert this mass in AMU into energy in MeV? By multiplying this by 931.5. If you multiply this by 931.5, then your answer will be in MeV. Solve this equation, find out its numerical value, and it comes out to be 0.78. 0.78 MeV. 0.78 MeV. So this is the answer of this question. Now come to question number 3. Calculate the Q value for 13Al25 to 12Mg25 decay. The masses of 13Al25 and 12Mg25 are given here. So what is this equation? First complete this equation. This is 13Al25. This decays into 12Mg25. And this is a beta decay. This will be a beta decay process, and this will be minus 1E0. This is positron emission or beta plus emission. Plus this will be neutrino. So this is the complete equation. This is a positron emission process. For the positron emission or beta plus decay, Q value is given by mass of the parent nuclei. So here this will be mass of aluminium nuclei minus mass of the deuter nuclei. This will be mass of Mg minus 2 times mass of electron and multiply this by C square. So this is the formula for the Q value. This is the formula we have already discussed, that this is the Q value formula for beta plus decay. Now substitute these values. All the masses are given here in AMU. So mass of aluminium, 13 aluminium 25 is 24.990429 minus mass of this Mg nuclei This is 24.985837 minus 2 times mass of electron. 2 times mass of electron. What is the value of the mass of the electron? We can separate it out. So first we are taking these two terms. These are in AMU. If you multiply this by 931.5, then this will provide us the answer in MeV. So what we have done here, we have splitted this into two brackets, MAL minus mass of Mg into C square minus 2 times MEC square. Here, if these masses are given in kilogram, then we will use this formula. We will multiply this by C square. But here these values are given in AMU. We can directly convert this into energy just by multiplying this 931.5 MeV. So this will be this one minus 2 times this MEC square. This is the rest mass energy of the electron, and this is equal to 0.51 MeV. Rest mass energy of the electron is 0.51 MeV. Solve this and you will find out the answer. Answer is 3.255. 3.255 MeV. If you solve this equation, you will find out this answer. So this is the Q value of this beta plus decay process. Now come to question number 4. In question number 4, in the decay of 14C, beta plus particle is emitted with the endpoint energy of 0.155 MeV. A beta particle with an energy of 0.025 is emitted in a direction of 135 to the direction of motion of the recoil nuclei. Calculate the momentum of the 3 particles involved in this process. So what is happening here? This 14C nuclei, this is decaying. This is decaying into the deuter nuclei. And along with this deuter nuclei, one electron is emitted, beta plus positron is emitted, and neutrino is emitted. Initially the nuclei is at rest. Initially this 14C nuclei is at rest and it is converted into 3 nuclei. This is decaying into 3 nuclei. So automatically resultant momentum of all these 3 nuclei will be 0. So we have 3 particles on the right hand side. One is recoiling nuclei or the deuter nuclei, second will be positron, and third will be neutrino. And total momentum, resultant momentum of these 3 particles will be 0. This beta minus particle is emitted in a direction of 135 to the direction of motion of the recoiling nuclei. Suppose I'm drawing a picture here. Suppose this is the recoiling nuclei, and this recoiling nuclei is suppose moving in this direction. This is the direction of recoiling nuclei. This is recoiling nuclei. This is the nuclei, and recoiling nuclei is moving in this direction. Recoiling nuclei means deuter nuclei. This is moving in this direction. A beta particle is emitted in this direction. This is beta plus particle that is emitted, and it is emitted in such a way that this is making an angle 135 with the direction of recoil nuclei. And suppose this third particle, neutrino, this is emitted in this direction. I am just assuming this. This is the direction of neutrino. So I will draw like this. I am drawing these perpendicular lines. So here this angle is suppose theta. This angle is theta. this angle will be 45 degrees. So this is the situation. So a nuclei decaying into 3 particles, recoiling nuclei, beta plus and neutrino. Suppose this is the direction of recoiling nuclei. So this beta particle is emitted in such a direction that these two directions are at an angle of 135 degree. With respect to each other, I have assumed that this is the direction of this neutrino. Neutrino is moving in this direction. Now we have to find out the momentum of all these 3 particles. Now our objective is to find out the momentum of all these 3 particles. What is given to us? They have given to us the endpoint energy. So what is endpoint energy? Endpoint energy is the, you can say, this is the kinetic energy of beta particle plus kinetic energy of this neutrino. This is known as endpoint energy. This is given to us. This is 0.155 MeV. This is 0.155 MeV. And now, beta particle with an energy of 0.025. So what is this? This is K beta. K beta is 0.025 MeV. So this is the kinetic energy of beta particle. Kinetic energy of beta particle. What will be the kinetic energy of this neutrino? From these two equations, we can write that K nu is 0.155 minus this 0.025 MeV. 5 minus 5 is 0. 5 minus 2, 3. This will be 0.130 MeV. This is the kinetic energy of this neutrino. Now we have to find out the momentum. For momentum, first I am writing down the total energy of this neutrino. This is total energy of neutrino. This will be equal to rest mass energy of neutrino m nu c square plus kinetic energy of neutrino, and this will be equal to P nu square C square plus M nu square C to the power 4. Here you are aware that this mass of the neutrino is negligible, so this will be 0, this will be 0. So what will be the value of P nu? So from here, P nu will be equal to kinetic energy associated with this neutrino divided by C. This will be the value of P nu. So P nu will be equal to kinetic energy divided by C. So this will be equal to 0.13. This is 0.13. This will be, you can write it as 0.130 MeV by C. This is the momentum of this neutrino. Second is, we have to find out the momentum of beta particle. What will be the momentum of beta particle? Momentum of beta particles. Here kinetic energy of this beta particle is half m electron, mass of electron, into, or you can write it as K beta is equal to P beta square upon 2 times Me. So P beta will be equal to 2 times K beta into this Me. This Me. Here if I multiply this Me by C square, so automatically I will have C here. So I multiply this denominator and numerator by C, and this will be this term. Basically this is, what is the unit of this MEC square? This is 0.51 C. Substitute these values here. Substitute, this is 2 times, what is the value of K beta? 0.025. This is 0.025. This is MeV multiplied by rest mass energy of the electron 0.51 MeV divided by C. If you solve this, then you will find out P beta comes out to be 0.159. This will be equal to 0.159 MeV by C. So this is the momentum associated with this beta particle. Next we have to find out the momentum of this deuter nuclei. What will be the momentum of deuter nuclei? So to find out the momentum of this recoil nuclei or deuter nuclei, basically we will apply the conservation of linear momentum in two directions. One along this line and in the perpendicular direction. So first I am applying the conservation of linear momentum in perpendicular direction. So this will be component of this momentum of this beta particle along this direction. So this will be P beta. This angle will be 45. P beta sine 45 degree will be equal to P nu E, and this will be sine theta. Substitute these values. This will be 0.159 into 1 by root 2. This is P nu E is equal to 0.130, and this will be sine theta. Now solve this equation and find out the value of theta. Solve this equation and find out the value of theta. This comes out to be 59.86. This is 59.86. This is the value of theta, 59.86 degree. Now with the help of this angle, we can find out the momentum of this recoil nuclei, apply the conservation of linear momentum along this horizontal line. So suppose momentum of this recoil nuclei is PD. So I am writing it as PD. I am writing the equation PD. This will be equal to P beta and component of this along this direction. This will be P beta cos 45 degree. Plus this will be P nu E, this will be P nu E, and this will be cos theta. And cos theta is this cos theta, this theta is here. This theta, you can find out this value of theta here. Substitute the value of P beta, P nu E and theta, and you will find out the momentum of this recoil nuclei, PD equal to 0.1781. This will be 0.1781. This comes out to be 0.1781 MeV divided by C. So this is the value of PD, the momentum of recoil nuclei. So in this way we have find out all three momentums. Momentum of beta plus particle, momentum of this recoiling nuclei, and momentum of this neutrino. Now come to question number 5. This is related to gamma decay. This is a very important question from exam point of view. Here 4 options are given, 4 pair of transitions are given, and we have to find out the possible multipole transition, name of the possible multipole transition. One by one I am going to discuss. Here take the example, first A part solution. So first I am taking this transition 5 by 2 plus 2 3 by 2 plus. So here first what we have to observe, first we will observe here, we have to observe that parity, either parity is changing or not. So here parity is positive, here parity is positive. So change in parity is represented by, so change in parity is no. So there is no change in parity. First thing is this. Second, we have to find out the allowed values of L. we have to find out the allowed values of L. So this is J. So what is the J value for the parent state? This is 5/2. What is the J value for the daughter state? This is 3/2. So here, what will be the possible values of L? Allowed values of L. This will lie according to this formula, Jp minus Jd and Jp plus Jd. This is the formula for the allowed values of L. From this formula one can calculate the allowed values of L. So here this will be mode of 5/2 minus 3/2, and here this will be 5/2 plus 3/2. So 5/2 minus 3/2, this will be 1, and this will be 4. So possible values of L lies in between 1 and 4. So what are the values of L which are allowed? This will start from 1, it will have 2, it will have 3, and it will be up to 4. So these are the possible values of L. So when we are choosing the value of L and there is no change in parity, then what type of multipole transition is this? So corresponding to L equal to 1 and no change in parity, this is M1 type of transition. It represents that this is M1 type of transition. This L equal to 2 corresponding to no change in parity, this is E2 type of transition. Now L equal to 3, there is no change in parity, this will be M3 type of transition. L equal to 4, no change in parity, this is E4 type of transition. So these are the possible transitions. These are the possible transitions for A part. Now come to B part. Now come to B part. In B part, transition is 3/2 minus 1/2 minus. Change in parity is there or not? So here parent nuclei has negative parity, daughter nuclei also has negative parity. So there is no change in parity. So delta pi is no. What is Jp? This is 3/2. What is Jd? This is 1/2. So what are the possible values of L? Possible values of L will be from 3/2 minus 1/2, and L values will be in between these two limits. This will be 3/2 plus half. So here L will lie in between. Here 3/2 plus 1/2, this will be 2, and 3/2 minus 1/2, it will be 1. So allowed values of L will be equal to 1 and 2. Now take the case of this L equal to 1 and there is no change in parity. So the allowed transition, this transition will be M1. It will be of M1 type. When you take L equal to 2 and there is no change in parity, then you are aware that it will be corresponding to E2. This will be corresponding to E2. So this is B part. Now come to C part. Here the transition is 3 minus 2 plus. So parent nuclei has negative parity, daughter nuclei has positive parity, so parity is changing. So here this delta pi is yes. In earlier two examples, parity was not changing, but here parity is changing. Yes, parity is changing. What is Jp? It is 3. What is Jd? This is 2. So what are the possible values of L? What are the possible values of L? It will lie in this limit. This is 3 minus 2. and this will be 3 plus 2. 3 plus 2 is 5, and 3 minus 2, this is 1. So allowed values of L is 1, 2, 3, 4 and 5. Now take one by one. For L equal to 1 and parity is changing. L is equal to 1 and parity is changing. So this is E1 type of transition. Now L equal to 2 corresponding to change in parity, this will be M2. Now L equal to 3 corresponding to change in parity, this will be E3. L equal to 4 will be M4 and this will be E3. So these are the types of possible multiple transition in case 3. Now come to the last one, D part. This is D part. Transition is given 1 by 2 minus to 1 by 2 plus. Here parity of daughter nuclei is minus, parity of parent nuclei is minus, for daughter nuclei this is plus. So parity is changing, delta pi is yes. Yes, there is a change in parity. Yes, there is a change in parity. So what can be the values of L here? L values will be here. This will be 1 by 2. This will be 1 by 2 minus 1 by 2. And here this will be 1 by 2 plus 1 by 2. So L will lie in this limit. This is 0 and this is 1. So L can have these two values, 0 and 1. But here we have to remember that this L is corresponding to photon and photon is a boson. So this L equal to 0 is not possible. This is not possible. This is not possible, as photon is a boson. So this is not possible. So only one value is there. There is one possible value L, and parity is changing. It means this transition is corresponding to E1 type. So the name of this multiple transition is E1. In this way we have find out all the possible multiple transitions in all the 4 cases.